Okay, hi, my name is Emily, and here's my chapter 14 portfolium. So, chapter 14 is an introduction to derivatives and how we can apply them to other concepts. So, the way we derive a function with multiple variables is using partial derivatives. And by that, we just set one variable as a constant and we look at the other variable and we see how z changes as the other variable changes. Graphically, it looks something like this. In a certain direction, for example, in the direction of x, we can see that at point A, we move from the contour line of 58 to 62 as we increase x, which shows that the derivative is positive because we're increasing the z value as we increase x. And then we can see that also with just the graph. Um, so the way we calculate partial derivatives is just by treating one variable as a constant, and we derive in terms of the other variable, and then all we have to do is plug in the points here for this problem, and we can get the partial derivative and the slope at that point. So next we move into local linearity, which tells us that if we zoom in on a graph enough, it looks like a linear function. And this allows us to approximate points on a function. And graphically, it looks sort of like this. We have a point of contact and the tangent plane which is the equation we use to approximate points at that certain area. And here there's an application. And then here on this slide, we have basically how we find the tangent plane, which is pretty much the same as we would with a function of just x. Okay, so after those three sections that were sort of just an introduction, we move into gradients and directional derivatives. So the gradient vector shows us the direction of the steepest ascent of a curve, and we have that here. And it can be used to find the directional derivative, which is the rate of change of the curve at a point in a given direction. And we do that by taking the dot product of the gradient vector and the given vector as a unit vector. So the unit vector is giving us the direction, and the dot product shows us the growth of the gradient vector in that direction. And here's a little bit of an explanation on why the gradient shows us the direction of the steepest rate of ascent. And we know that the max value of fu occurs when theta equals 0, because then u and the gradient would be pointing in the same direction. So if we set theta to 0, the expression just evaluates the gradient of f. And the magnitude of this vector gives us the greatest rate of change because it shows the size of the vector. And since u is parallel to the gradient, the magnitude is also the value of the directional derivative. So something else we notice is that the gradient is perpendicular to the level curves on a contour diagram. So in this case, if we look at the level curve a point is on, so here, and then the next curve, then we see that the tangent lines are parallel to each other, and the tangent lines of this function are just the same thing as the contour lines. And since the lines are parallel, the direction of the greatest increase will be perpendicular to both of them because it's the shortest distance between the parallel lines. And then we can use that same reasoning to see why a function of x, y, and z has a gradient perpendicular to the level surfaces. So we can find the equation of a tangent point, plane at a point in two different ways. So this way is the way we learned earlier. And then there's also this way. And what we're doing here is basically subtracting z from one side and finding partial derivatives of all three variables. So we can do that because the tangent plane is perpendicular to the point, and since the dot product of two perpendicular vectors is equal to 0, we take the dot product of the gradient vector and points on the surface, and we set it equal to 0. And this gives us the equation for the tangent tangent plane. So next we move into the chain rule, and here's a little bit of an intuitive sort of explanation on how that works. And basically it's the same thing as it is in two space, where we just take the derivative of the outside function, multiply that by the derivative of the inside function. And here's sort of just a looking at equations and how we use the chain rule here. And then we also have a graphical representation of how the chain rule works. So these are like the inner functions, and we have the change of the outer functions. So we can just plug the inner function changes into the equation and solve for the change of the main function c. So then we can look at second order derivatives, and we can take the second order derivatives we end up with 4 of them, with xx, yy, xy, and yx. And as you can see, xy and fyx actually turn out to be the same thing. And if we look at it this way, we can hold y constant. And if we take fx, it's taking a slice parallel to the xz plane, and then we're finding the slope. And the second order mixed derivative, xy, is the rate that this slope changes as x changes in the y direction. And if the function is smooth, then the other mixed partial derivative will be the same. Okay, so we can use second order derivatives to approximate functions with Taylor approximations. And we do this because this is sort of the equation we use. So we can just plug in what we have for the second order derivatives into the equation. And for concavity, if the second order partial derivative is positive, then the graph is concave up, and if it's negative, it's concave down. So in this situation, at 0, 0, we can see that the graph is concave up, and we can see here of fxx, the graph, the second derivative evaluates to being positive, and that lines up with the graph. Okay, so the last concept we look at is differentiability, and 2 pretty intuitive ways to do this is using features of the graph. So you can see we have this function here, and you can see along the x and the y axes we get these corners, and we know that it's not differentiable at these corners because there's 2 different slopes approaching that point. And then also, if we take the partial derivatives, we see that the derivatives evaluate to being undefined when x and y are equal to 0. So the basic concepts about chapter 14 are just derivatives of functions of multiple variables, how we can apply them, and then other common concepts that we need to learn, we need to know for other applications. Thanks.